Hello and welcome back to Partial Differential Equations, the video series where we tackle a lot of different problems in analysis. Indeed, in today's part 4, we will continue our discussion about Laplace's equation where the solutions are called harmonic functions. And there it turns out that these functions satisfy a mean value property. And what this exactly means I will tell you soon, but first I want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And please don't forget, as a member on Steady or Patreon, you have access to all the additional material for the videos. For example, you can download PDF versions, quizzes and books. And then without further ado, let's immediately start with the content of today, which is about harmonic functions. And there, as we have already discussed before, it's just a function u that is 2 times continuously differentiable and satisfies Laplace's equation. This means if you apply the Laplace operator to it, you get out 0 on the whole domain omega. So in the formula we would write Laplace u of x is equal to 0 for all x in omega. And usually this domain omega should be an open subset in Rn. And please check out the last video to see some examples for omega and u. Here we will stay completely general and show that every harmonic function has a really nice property. This is the so-called mean value property, and we will formulate it as a theorem. And the assumption here is quite simple, we just take a harmonic function u defined on omega. Hence the codomain is just given by the real number line. And now, since omega is given as an open set, we know that for every point in omega we find a whole ball around it. And it's possible to choose the radius of the ball so small that the whole ball lies inside omega again. And let's say that we call this chosen radius capital R. So the ball is BR centered at x0. And now first we want that this open ball lies completely in omega. And this is always possible because omega is an open set. But then in that case we can make the radius r even a little bit smaller, and then we can say that the whole closed ball lies in omega as well. And indeed this is what we want to have here, because I also want to integrate over the whole boundary of the ball as well. Indeed, it turns out that integrating over the whole boundary of the ball is already enough to fix the value of u at x0. In other words, u of x0 can be calculated by an integral. And as already mentioned, this will be a surface integral over the sphere. It's denoted by srx0, which means it's the n-1 dimensional sphere in Rn with radius r and centered at x0. And in fact, this is exactly the boundary of our closed ball here. And now we just have the surface integral of u d sigma. And the only thing missing here is that we have to normalize this integral, so we divide by the n-1 dimensional volume of our sphere. And as always I just write volume, but you know it's the generalized area of this sphere. So you see what we calculate here on the right hand side is just a mean value because we integrate over all the values of u on the sphere. And now this mean value that just uses the values here gives us exactly the value at the center at x0. And that's why we call it the mean value property, because the value of u at x0 is completely determined by the values at the sphere. So it's a really special property, and it's quite surprising that the harmonic functions do that. And in fact it will take a little bit of time to prove the whole statement. And first I want to define the function on the right hand side. Let's call it capital F. In fact, we can see the right hand side as a function depending on the radius r. So if you want, we can also consider a smaller radius. Of course, if capital R works, then every smaller ball also lies completely in our domain omega. This means f of any radius smaller than r is well defined. We can just use the same integral formula as above. The only difference is now that we use a lowercase r. However, we can only do that for a radius that is smaller than capital R, but it cannot be 0. In that case, the sphere does not make much sense, and we can also not divide by the volume but we already know the value we want to have at this point. Namely, if we see it as a mean value and we only have one value, then this should be equal to u of x0. Hence, in that case, also the exceptional case is defined. And now you already know what we actually want to show is that this function F is actually equal to u of x0 also in all the other cases. In other words, we want to show it's a constant function. And there we can go step by step, and the first thing we show, it's a continuous function. And maybe the continuity is only really interesting at the origin, because for the other cases, it might be really obvious that we have continuity. If you don't see that directly, you will definitely believe it after the discussion of the next part. Therefore, let's first focus on showing the continuity at the origin. So we check the distance between f of r and f of 0. The first term is given by an integral, while the second one is just a constant. But obviously also a constant can be written as an integral. So what we do is that we use exactly the same formula, but instead of u, we use the constant u of x0. And there you should see, this term is exactly u of x0, because we can pull out the constant, and then these two things will cancel to 1. So it's a more complicated formulation of a constant, but it helps us because we can push the two integrals together. So we just have one integral where the distance of the two functions is inside. So this is quite nice, and then in the next step we can use the triangle inequality for the integral, which simply tells us that we can pull in the absolute value. Hence now we just have to estimate the value inside the integral. And a really rough estimate is already good enough. It means just use the largest value you can find for the function inside. So we can just use the supremum norm and pull this term out. Therefore, this is the supremum norm of u minus the constant. And to be precise, the supremum norm is actually only taken with respect to the sphere with radius r. And then what remains on the right hand side is just the integral where we integrate the one function. And there you see the surface integral here is exactly our generalized volume of the sphere. So this completely cancels and only the supremum norm remains. And now what we want to do is to make our variable r smaller and smaller, which means the sphere gets closer and closer to x0. So obviously the supremum norm here has to go to 0 when r tends to 0 as well. So obviously there we have to use that our harmonic function u is a nice continuous function. So that was the first step. We have a continuous function F. And now in the second step, I want to show that we actually have a differentiable function. And in order to see that, it might be better to put the dependence on the radius r inside the integral. So this just means that in the mean value we want to calculate, we have to do a substitution. And first of all, we can translate the center of the sphere to the origin. This is quite simple, we just have to translate by the vector x0. And then inside the integral we have u of x0 plus a new variable y. So not so complicated, the y variable just goes over the sphere here, and then you see this is actually exactly the same integral. And then in the next step I want to shrink or expand our ball to the unit ball. And in order to see what happens then, you can use spherical coordinates, also called polar coordinates. The integration with respect to these coordinates is not so complicated and something I have already discussed in another video. Maybe there the important part is just that instead of y, we can use a unit vector that we call omega. And then if we stretch omega by the radius r, we also actually hit all the points on the sphere from before. However, the stretching by r happens in n-1 dimensions, so we get the scalar in front as well. More precisely, using the substitution, we get in the factor r to the power n-1. So this is important, and if you want to see the details about that, you can watch my multidimensional integration course. It's the part where we discuss the integration with polar coordinates. Okay, so now you see we have transformed the formula here, and now r is not in the integration domain, but inside the integral. And to form the function f, you know we also have to divide by the volume of the sphere. And also there you might know that this generalized area scales with the same factor r to the power n minus 1. More concretely, you just need to know the volume of the unit sphere and then you can scale it to get all the other volumes. However, there the implication is that this factor r to the power n minus 1 will cancel for our function f. So we just have the integral from above and we just divide by the unit volume. This is quite nice because it shows us that the dependence on r is only given inside the function u. And since u is a harmonic function, we already know that the differentiability is not a problem at all. Indeed, the only thing that might be in the way when you want to calculate the derivative of f is this integral. But this is not a real problem because here it's actually allowed to push the limit of the differentiation inside the integral. And the standard justification for that would be to use Lebesgue's dominated convergence theorem. And if you don't remember that, please check out my video about it. Here we don't need the details, we just need to know that we can calculate the derivative of our function f. And as already mentioned, this one is done by pushing the derivative inside the integral. And there we can finally use our knowledge about the derivatives of u. Namely, this whole thing here results in applying the chain rule. There the outer derivative is the gradient of u and the inner derivative is just given by omega. Hence what we get is an inner product of these two things. So the gradient can be written as nabla u and then we have it in the inner product with omega. And if you see such a combination like that, you should know that this is actually a directional derivative. More concretely, here we have the directional derivative of u along the vector omega. And you should see that this happens on our surface, so on a point of our sphere. And the radius is still r, so for example we land here. So in the picture, this vector here is r omega, and omega itself goes in the same direction. So it's a nice unit vector that is also normal to our surface. And exactly this special directional derivative is what we sometimes also call the normal derivative on the surface. The direction is exactly perpendicular to the surface and this makes this derivative special. And a short notation which is quite common is to write the partial derivative with respect to the direction n of u. And here in our context, capital N is exactly the same as omega. And now the advantage of this normal derivative is that we can apply Green's identity to our function f. More precisely, we can just use Green's second identity, which holds for C2 functions. This one you can also find in my multidimensional integration course, and it connects a volume integral with a surface integral. And indeed, here we would use our ball, where the boundary is given by the sphere. And obviously instead of g, we would use our harmonic function u, and instead of f, we can use the constant 1. Because then you see on the right hand side, we have exactly the combination we want, namely just the normal derivative for u. Okay, so to reach the goal, let's put everything together. So first we know that our f prime is given by the normal derivative of u. We integrate over the unit sphere, but you see we evaluate this normal derivative at the point of our bigger sphere. In other words, we can just do the same substitution as before, just backwards. Hence we get our integral back over the original sphere with radius r. And there please don't forget, as before, in the substitution we also get the factor r to the power n minus 1. And then inside the integral we just have our normal derivative of u evaluated at a point on the sphere. So in short, we can just write d sigma as before. And finally at this point we can use Green's identity to put in the Laplacian of u. So we have the same factor in front, but then we get a volume integral over the ball. But this does not matter so much because inside the integral we find the Laplacian of u. And there we can use the assumption that we have a harmonic function, so we know that the Laplacian of u is equal to 0 on the whole ball. So the conclusion here is, no matter which radius r we choose, this derivative of f is always equal to 0. So we have a differentiable function defined on an interval with vanishing derivative, and this definitely implies that we have a constant function. And this is exactly what we wanted to show. For every radius r, the value of f is the same as at the origin. And by definition, f of 0 is exactly u of x0. So this shows the mean value property of harmonic functions. And I can already tell you, in the next videos we will look what we can actually do with this nice property. So I really hope I meet you there again, and have a nice day. Bye bye.